Hello and welcome to this class on total internal reflection. This is a demonstration class and this is being done so that our teaching methodology can be demonstrated. Let me start by summarizing what our teaching methodology is. In an earlier video, I had described the teaching methodology. It consists of 5 elements, and here they are, just to summarize what our methodology is. The first element is that we should present an integrated view, a holistic view of the concept that we are teaching. The second element is that we show simple demonstrations and experiments in order to make the concept easy to understand. The third element is that we have to connect recent developments in science and technology to the concept. The fourth element is that we identify practical applications of that concept. And the fifth element of our methodology is we try and connect it to values or ethics wherever possible. So all of these elements are an integral part of our teaching methodology. Now let us see how these elements can be applied in the teaching of total internal reflection. Now, many students or most students in high school are aware that when light travels from one medium to another, refraction occurs. Refraction essentially is the direction of the ray of light changes when light goes from a denser medium to a rarer medium, or from a rarer medium to a denser medium. Now, when light travels from a rarer medium to a denser medium, as we have illustrated here, most students know that the refraction happens towards the normal. So let's see what happens when light goes from a rarer medium to a denser medium. So if we have a ray of light, the red arrow in this presentation, which is normal to the surface, then there is no refraction. The refracted ray is also normal to the surface. Now, as we change the angle of incidence, you can see that the refracted ray is bending towards the normal. As we increase the angle of incidence, in this particular example, the angle of incidence is here. And this is the angle of refraction. This is the angle of incidence. And as we increase the angle of incidence, you can see that the refracted ray continues to bend towards the normal. And in all these situations where light is going from a rarer medium to a denser medium, the angle of incidence is more than the angle of refraction. And that is something you can observe in all of these situations. Now, what happens when light goes from a denser medium to a rarer medium? Let us see what happens. You know, you have read in your textbooks that when light goes from a denser medium to a rarer medium, the ray of light after refraction bends away from the normal. Let us start, like we did before, with a ray of light which is normal to the surface. In that case, there is no change of direction. The refracted ray is also normal to the surface. And as we continue to increase the angle of incidence, you can see that the refracted ray is bending away from the normal. In all of these examples, you will realize that this is the angle of incidence and this is the angle of refraction. And in each of these cases, R is greater than I. The angle of refraction is greater than the angle of incidence. So what happens as I continue to increase the angle of incidence? There is a point where the angle of refraction becomes 90 degrees. What does it mean? the refracted ray goes along the length of the surface. So this angle becomes 90 degrees. Now, there is a certain angle of incidence I for which the refracted angle becomes 90 degrees. Now, if I have to draw a diagram or to illustrate this on the board, let us see what it looks like. I have a trough of water here. This is water. And I shine a ray of light in this way. And it bends away from the normal. This is the angle of incidence. This is the angle of refraction. You can see that the angle of refraction is bending away from the normal. Let me draw a bigger picture to illustrate this. Now, as I increase the angle of incidence, and this is the normal, there is a point where the refracted angle goes along the surface of the water. And if I increase the angle of incidence even more, there is no longer refraction, but the light becomes reflected. And that is what we call total internal reflection. So the ray of light, instead of getting refracted, becomes reflected back into the water. And that is what we call total internal reflection. Now, it is possible to do a very nice and simple demo of this phenomenon, which I will show you. And it is very easy to do at home. So let's do it. So here we have a trough of water. And I will be shining a ray of light through it. Observe the pattern that the light makes. You see a triangular pattern emerging. Now, what happened here was that the incident angle was such that the light got reflected back into the water and reflected again, forming a triangular pattern. So total internal reflection has occurred twice. Once it occurred here and once here. So this pattern was possible because of total internal reflection. Let's continue with our presentation. So the angle of incidence at which the angle of refraction becomes 90 degrees is called the critical angle. So you can see here in this calculation that at the critical angle, the angle of incidence can be called IC and the angle of refraction is 90 degrees. So using the formula, we can calculate the refractive index of glass with respect to air. Let us talk about a natural phenomenon called mirage. A mirage is a phenomenon where on a hot day, perhaps in a desert, you will see things that do not actually exist. You may see a pool of water, or you may see other images on the hot sand, but there will not be a pool of water there. It is just a reflection. Now, how is that explained? Now, let us look at this particular picture. We have a desert on a hot day, Uh, there is a traveler standing uh, to one side, and we have a couple of trees. Let us see what happens in this case. There is a ray of light going straight from the top of the tree into the man's eyes. Now, when you look at the tree, you are able to see it. And that is possible because a direct ray of light is going from the tree into the man's eyes. There are many rays of trees reflected from the tree. Let us look at one other ray of light and see what that does. Another ray of light going in that direction, what does it do? Remember that the desert sand is very hot, and the air which is in contact with the desert sand is hot. And as you go further away from the hot sand, air is cooler. So the layers of air further away from the sand are cooler compared to the layer of air in contact with the sand. So what does light do? Remember, cooler air acts like a denser medium, and warmer air acts like rarer medium as far as light is concerned. So this ray of light of ours, as it passes through the many layers of air, it goes from cooler layers of air to the warmer layers, each time undergoing refraction. And at this particular point, the angle of incidence is greater than the critical angle, and therefore there is reflection. And now it gets reflected, and this ray of light enters the man's eyes. So what the man sees looking down is a reflection of the tree here. It appears as if there is a tree here. So what he's seeing is an image of the tree because of total internal reflection. And why did it happen? It happened because a ray of light starting from the tree got refracted, total internal reflected here, and then ends up in the man's eye, causing him to think that there is a reflection of the tree in the sand. This is a natural phenomenon explained by total internal reflection. There are many practical applications of total internal reflection, one of which is in communication. Now, you must have heard of optic fibers. A ray of light can be used to transmit information through a glass pipe. Now, information flows through the glass pipe, much like water would flow through a pipe, and it goes through the pipe. We are told that light travels in straight lines, but how does light follow this curved pipe? It is possible because of total internal reflection. A pulse of light is going through the pipe, even though the pipe is not straight. That happens because every time the light hits the edge of the pipe, there is total internal reflection. And that causes the light to follow the pipe. And this is used in telecommunications. You must have seen several of our roads being dug up because they are laying optic fibers. It causes a lot of inconvenience to people, but the intention is to lay optic fibers and improve our telecommunication. So you saw that in this particular discussion on total internal reflection, we talked about a holistic or an integrated view. We spoke about the way light behaves as it moves from one medium to the other. There was an experiment conducted to show how total internal reflection can be demonstrated so easily. We spoke about engineering applications. So there are all of these aspects which are connected as part of our teaching methodology. Thanks for watching.